place, they are true in the cohomology of the pure braid group. Now we need to prove that these are all relations, and it is sufficient to prove that these additive bases, that these elements, so what we actually need to prove, we need to prove that these elements, monomials of such type, are linearly independent. This is first. And second, then it immediately follows that we have no other relations. The matter is that these monomials are indeed bases of this ring. This is a simple algebraic fact that these monomials form basis of this ring. So if we took further quotient, if we had some additional relation, then they will not be linearly independent. But they are linearly independent, so if we prove that they are linearly independent, we immediately obtain that there are no other relations, but still we need to understand that additionally we need to understand that this is the whole cohomology ring, that we do not have some that this omega KL generate the whole cohomology ring. Okay, last time I started to prove this fact, but I'm very sorry. At some point, I was slightly in a hurry. Initially I wanted to finish the proof last time, but at some point I said wrong. Well, I just confuse in my which of the group is normal. This one is normal and this is not. And so I tried to conjugate elements of this group by means of elements of this group. And this makes no sense. We need to conjugate these elements but by that one. So now the idea is the same, but and now I do it more in correct way. Well, first of all, we prove all these things by induction on n. And we have checked that this is true for n equal 2, so we have base of induction. And now we assume that we know all these things for n minus 1. What does it mean? It means that, okay, we have here some basis for n minus 1. We have basis in homology also with integral coefficients. These are free abelian groups. And we have basis here, which is dual to these bases in cohomology. So in cohomology here, we have basis consisting of all such monomials, but okay, well, for n, we have here less than equal to n. But for n minus 1, we of course have, here we have basis in cohomology consisting of all such monomials with properties that ki less than li, and these are strictly increasing and less or equal to n minus 1. This is basis here, and here we have dual basis. I don't want to invent some cumbersome notation for this dual basis. Just we have some elements which are dual to these monomials. Okay, but look, these elements certainly are we can consider same monomials with these conditions here in Pn. And of course, they are pullbacks of those monomials in Pn minus 1. Since, well, they're just the same homomorphism. So, and here, of course, since the sequence splits, we can take this dual basis and put it to Pn, move it to Pn. Let this split and be F. So starting from this, we see that if I take, okay, I'll write it in the following way. If I take F star of this dual basis, then this is not the whole basis, but this is part of dual basis. These are elements dual to these monomials. So I would like to write down such matrix. These are values of cohomology classes on homology classes. So here here will be basis in homology, and here in cohomology. And if I put here this F star of dual basis for Pn minus 1, then, well, I have here all monomials of such kind with Ls less than n. And here I have all such monomials with Ls equal to n. Well, in some order. Just I write down all these monomials of such kind. And here, first I take all of them with Ls smaller than n, and then all with Ls equal to n. And then, since this was dual to these bases for Pn minus 1, what I have immediately? I have here is the identity matrix. And moreover, here is 0. Why? Because omega KL with L equal to n, its restriction to Pn minus 1 is 0. If the nth strand is straight, then such omega Kn do not enter to our group element, and such homomorphism are trivial. Homomorphism omega Kn are trivial on Pn minus 1. So all their products, all such products are also trivial when restricted to Pn minus 1, so here is 0. Well, this is what we have. This is just we have by induction. But I want to construct the second part. This is what we have not constructed yet. We want to construct some special basis in homology. And what I want, this part is what I have, but this is what I want. I want to have here unit matrix here, and actually it doesn't matter what I have here, since if it is upper triangular matrix, then of course I can easily construct a truly dual basis starting from this one. So I will not this is completely irrelevant for me. I will not consider this at all. So my goal is to construct such elements that here the matrix is the identity matrix. And well, now look how any monomial with Ls equals to n, well, okay, it has such form. Ks minus 1, Ls minus 1, and here we have some Ks n. Well, and these L's of course, they strictly increase. And so, of course, Ls minus 1 is smaller than n. So any such monomial, we have this monomial corresponds to, it still lives in cohomology of Pn minus 1. And we have this additional monomial. All these monomials are of such type. So starting from, these are my initial data. Starting from such monomial, and starting from this pair Ksn, I would like to construct an element here which have the following property, that an element in homology. I would like to, starting from this, I would like to provide some element, let it be Z, in homology. In homology, of course, in S homology of Pn with integral coefficients. And I want the following property. Let this monomial be M. I want that the value of monomial M on Z is 1, actually, plus minus 1 is enough for me. I don't want to think about signs. And for any other monomial, I would like to have 0. For any other M prime of the same type, I don't want to think about these monomials. It is not important for me. Okay? For any other M prime of this type. Well, this is my goal. And now I want to construct such monomials. And okay, to construct it, I introduce some special operation in bar resolutions. Not monomials, I want to construct these homology classes, such homology classes. This operation resembles very much what we did on the previous lecture, but these two roles of these two groups are reversed. I'm sorry for this.
The monomial of this type means that we can change
other L's, other Ks, but still the last one is N. And for all monomials, these L's strictly increase and K's are smaller than L. This is always. I consider only such monomials.
Yes, and S is a constant.
S is a constant since just, of course, if I took elements of different degrees, they appear in 0. I just don't need to think about it. So yes, so we may assume that S is constant. Well, for a moment, I want to consider now I want to describe one construction. In this construction, it is not important that these are these particular groups. Just it is important that we have some semi-direct product of groups. So for a moment, I consider general situation, and then we return to this particular. So let us consider a split short exact sequence of groups. Split, it will be important for me that it is split. So it is a semi-direct product. G is semi-direct product of H by Q. H is normal, but Q is not, generally not. And I would like, okay, I recall that I have 3 bar resolutions. I have B star of G. This is bar resolution. Normalized, non-normalized, this is not important for me. Same for H and for Q. These are bar resolutions. And I recall that, okay, if we speak about integral homology, homology with integral coefficients, then these are for instance, homology of G with integral coefficients. It is homology of the following. We need to take bar resolution, and we need to take coinvariance. So we need to tensor by Z over ZG, which is, this is just by the same. Coinvariance is the same as to say that we take this. And similarly for H and for Q. And I would like to introduce the following operation. I will call it shuffle. It is from complex which computes homology of H and tensored by same complex for Q, and it goes to the same complex for G. And I will write down this operation by very particular formula. And it is very similar for what we have written last time, but once more we reverse the roles of H and Q. So if I would like, I just write it down on basis elements of this. So if I take a basis element of this bar resolution for H, but okay, this is not in bar resolution, but this is in coinvariance. So when I will write differential, H1 will not go here. It will just be omitted. The differential in bar resolution starts with, I just want to recall, it will be important for me. The differential in bar resolution starts with the first the first term is like that, but when we tensor it, when we take coinvariance, then this G1 disappears, of course. So in this complex, the first term is just G2, Gm, plus and so on. So we always live in coinvariance, not in bar resolutions themselves. Okay, so here I have several H. H's are elements of H. And here I have several Q's. Q's are elements of the group Q, Q large. And okay, it is not so easy to write down the formula, but it is easy to explain what I want. I want to, what is shuffle? Shuffle is, well, we take such permutations of these m plus n letters such that the order of H is the same and the order of Q's is the same, but they may shuffle in any possible way. So for instance, H1, H2, Q1, H3, Q2, and anything of such kind. We consider only those permutations that H2 can't go before H1, but H1 and Q5 can go in any possible order.
Signs?
Well,
What about signs?
any shuffle is a permutation, and it has sign.
Yes.
As a permutation, and they will go. These signs will be in our formula. Now, but we don't just take shuffles. We take clever shuffles. Clever shuffles are as following. The sum is all shuffles new. Here I put sign of new, and here I put just for instance H1. This is just some Q's are always put without any change. If in a shuffle I have Q, then it is put without any change. But if I have H, then here I recall that I recall it here that we have the following standard group notation. Such conjugation is here I put the sum of all Q's which are before it. Not the sum, the product of all Q's which are here. So if here the last Q is Qk, then we put here such power. But Q's are always without. To be precise, I would like to write down explicit formula for the case m equal n to equal 2. Just to be sure that you understand me properly. If I want to consider shuffle of what we wrote last time we wrote this for the case of only one Q, and also we reverse the role of H's and Q's. But last time only one Q was here, but actually we need any of them. If we have only two H's and two Q's, then it is not so hard to consider all shuffles just to enumerate all of them. Okay, we have this trivial shuffle, H1, H2, Q1, Q2. Sign is plus, since it is trivial permutation. Now, we may swap H2 and Q1. So we have H1, Q1, H2 to the power Q1, because before this H, we have Q1, and Q2. And sign is minus, since this is the sign of shuffle. Next, we have plus. We can swap these two also, H1, Q1, Q2, and here is H2 to the power Q1, Q2. Well, next, these are all where H1 is on the first place. Now Q1 is on the first place, and the first one is H1, Q1, Q2, and here I have H2 to the power Q1, Q2. Since we have, oh, so sorry, Q1, H1 to the power Q1, H2 to the power Q1. Both are to the power Q1 since we have only one. And okay, this is also plus since this shuffle has sign plus 1. Okay, now with sign minus we have Q1, H1, Q1, Q2, and before H2 we have both Q's, so H2 to the power Q1, Q2. And the last term is Q1, Q2, H1 to the power Q1, Q2, H2 to the power Q1, Q2. Okay, that's all. So we have such particular map. Of course, once we have written such map, the first natural and the most important question is how this map, what is the relationship between this map and differential? We have differential here, and differential here, and of course we are interested in what is the relationship between them. Okay, We can write it explicitly. And the answer is, well, the answer is not so difficult, complicated, but this is not enough to write down the answer. I think I erased this this picture, since otherwise I don't have enough space. Okay, so I would like to write down these. The differential of such shuffle. Tensor. Yes, of course. This is written on basis elements. Of course, by linearity, we extend this to the whole group. There is no problem with this. So I write down the formula, and then I explain that the formula is obvious. But okay, we have the following. We can shuffle the boundary of the first element with the second. Well, this is the first term. We also can shuffle this with the boundary of that. And this is like that. This is the same, but we have here sign -1 to the power m of shuffle of h1, hm with the boundary of q1, qn. Okay. And next, this is not all, but we have only rather simple correction. We can take shuffle of Q1 plays some special role. All h's are put to the power Q1, and here we have Q2, Qn, and minus the same without these powers. Okay, this is not very short formula. Actually, the formula which we proved last time, when we had this, we have proved the same formula with only one Q. We have proved this, but okay, now it is not so hard to understand why this is true. Look. When I consider all such shuffles and I start computing differential in this standard bar differential, how does bar differential operates? First term, we erase first term here. Then we multiply some two consecutive terms. And finally, we erase the last one. Look. If we multiply two consecutive terms, then there are three possibilities. It can be two Q's, two H's, or Q with H. Okay? Now, first of all, if it is Q and H, then look, for instance, it is Q, A, K, and the next element is some H, L, to the power, but then it is to the power q1, qk. And something before and, but together with this term, I also have shuffle which differs only in the order of these two elements. We always can consider this shuffle, and it will have, if here is plus minus, then this here the sign will be opposite. And what I will have together with this shuffle, I have this shuffle. Here is LGL, but to the power q1, qk minus 1, and here is qk. And if in both cases I erase this bar, I multiply, then the results are the same. The product of these two elements is equal to the product of their two elements. And the signs are opposite. So all such elements cancel immediately. They cancel just here in the left-hand side. We have no such elements. If we write them down, it is a good exercise to take, say, n equal 2 and to make this computation explicitly. But all such elements go. All of them cancel. Now we have elements where we multiply two h's, but they are all here. We can multiply two h's and then take shuffle, but we can multiply them before and then take shuffle. They are all here. We can multiply two q's, but they are all here. And this minus 1 to the power m is just okay. It is just a standard combination of the corresponding signs in bar differentials. The same is when we erase last term. Again, if it is last h, then it is here. If it is last q, then it is here. And with the first term, look, if we erase first h, then again everything is okay. But if the first one is q, then there is some difference. Again, we have this term both here and here. But here q1, I'm interested only in those terms when this q1 is deleted. But then I have shuffle of this product, this element with element q2, qn. Okay? But here I have another element. I have this q1 goes before. All h's are raised to this power, and only after that I delete this q1. So instead of this, I have this. This is exactly what has happened. So I hope I explained why this is true. This is a good exercise to do this precisely, to prove this formula precisely. But of course, well, I hope what I said is enough to do this exercise. Okay, now this is the main formula. So our shuffle was, look, it is important what was wrong last time. Last time was wrong that I took, well, if h's are from h and q's are from q, then these conjugates again belong to h. And this is very good. Otherwise, we cannot conjugate elements of q by elements of h. We get to, we don't understand where we get. But in this way, it is okay. Well, now let us return to our situation with braid group and apply this operator. Okay. Okay, now I just want to return to our situation. Our situation is that I have this particular short exact sequence, which of course splits, and I would like to construct particular element. I would like to construct this class Z with these properties. Okay, I will start constructing it. Okay, my initial data are as follows. I have this monomial, and I have this pair Ksn. For this monomial, I have an element of S minus 1 homology of Pn minus 1, which is dual basis element. By induction, I know that in Pn minus 1, I have dual basis for these monomials. So by induction, and I assume that there is some x, such x. And for this x, I would like to represent this x by an element in bar resolution. So I will consider C in bar resolution of, well, here I have S minus 1, since of Pn minus 1. This is Q, this is group Q, and coinvariance. Okay, I have this element whose homology class is X. That particular X, which is the dual basis element to this monomial. And here I would like to have, actually I can take any element on which this omega takes non-zero value, but I prefer to take particular element. I prefer to start with an element H. This is just an element of n. This is just Ksn. This is just generator. I know that the value of omega Ksn on this element is 1. Okay? And now, well, this is a group element, so to it I can consider, just for simplicity, I prefer to write down H here, since it is too large. Now I want to consider the following. I want to write down this is an element of the bar resolution for free group, and this is an element of bar resolution for, this is for H capital, this is for Q capital. So I can take such product, and I can take shuffle of such product. Exactly in that sense, what as I did. I recall that if H is somewhere in between, then I raise it to the power of all Q's before it. Okay, this is not our Z, but this is some initial part of our Z. I want to denote it by Z1, and now I would like to correct this to obtain that Z. Well, look, what is not, why I cannot take this Z1 for Z? The matter is that it is not a cycle. If I want to compute, well, look, this one and this one, they are cycles. We always have this. We always have this in any coinvariance of any bar resolution. I recall that in bar resolution we have the following formula, but in coinvariance this becomes 0. This is always. So that's no problems, and this is 0 since it is homology. It is representative of homology class. So when I want to write down dz1, then the first term here vanishes, and the second term vanishes, and only this third term is still here. So, okay, if I want to write it down, I need I need to be more precise. I need to write down xi as sum of some coefficients lambda I times qi1 qi s minus 1. Okay? Just we have sum of any element of bar resolution can be written in this form. Then dz1 is, we have only this term. So m is equal to 1. So we have just the following. We take sum over i's, lambda I. Here we have h minus h to the power qi1. Sorry. I want to write down it. Shuffle of h minus h to the power qi1, and here I have qi2 qis minus 1. Well, we have this particular formula. Look, now I want to explain what I want to do, what I want to have. I want to make this Z1 a cycle. It is not a cycle, we have not 0 here. I want to make it a cycle by adding to it some other shuffles of some pairs of chains, but it is important that in all these shuffles, I want to add only shuffles where here we have at least second degree, degree at least 2. So in this particular term, we have degree 1 here and degree s minus 1 here. I want to add something, and I allow to add any shuffles with any chain here and any chain here, but I require that all chains, all additional chains have degree at least 2 here. So
is degree the number of?
Yeah, degree is the number of these h's. So this is what I want. I want to find z, which is this particular z1, plus some any sum of shuffles of some alpha case and beta case. But my requirement is that the degree of each alpha k is greater than or equal to 2. And I want this z to be a cycle. Assume for a moment that I succeed to do this. I claim that this solves all our problems. Look, I would like to compute the value of this monomial on this particular cycle. But we have already discussed how to compute products in bar resolution. And the answer is the following, that it is very easy to compute a product of two cohomology class, of two cochains. This is just a general formula. To compute product of two cochains on some elements if the first one is of degree m and the second one is of degree n, then I just need to take minus 1 to this some sign, which is not so important. Just C1 on G1 Gm on the first m and C2 on the other. Very simple formula. This we have proved this. This is just some variant of Alexander-Whitney formula. So, look, if I would like, here I have product of one cochains. If I want to compute its value on any element in bar resolution, I just need to compute the value of the first on the first term. Well, if I have some such row, G1, then I need to compute the first homomorphism on the first element, the second homomorphism on the second element, and so on. Well, look, in all these shuffles, I have at least two elements from H, from here. This means, but all these terms, except for the last one, they vanish on H, on this free group. They are zero here. So this, independently on which alpha k's and beta k's are here, here we have always zero. But look, for this Z1, let us, let us write down this shuffle explicitly. Once we have this formula, what is shuffle of one element and s minus one element? I don't want to write down it explicitly. We can insert this H in any position. But again, if it is not on the last position, then the value vanishes. So the only term which can give a non-zero value is the last term. I don't want to, so it is, I am interested only in this last term. I don't want to carry about signs, since, okay, this is just this plus minus one. But the last term is where, okay, here we have all these Q's. And on the last term, we have H, okay, to the power of all these Q's, but it doesn't matter. Since the matter is that I want to compute homomorphisms to abelian group on this. And the value is just, I take this monomial on this element, and this is exactly the value of monomial on of this monomial of this first part. So the result is as follows. I prefer to write it here. The result is that the value of this monomial m, which is written here, on the z, first of all, only this term gives impact, and this impact is this plus minus, which I'm not interested in. Here I have the value of this. Let this starting part be m1. So I plus minus this m1 on x and multiplied by the value of the homomorphism of the last homomorphism omega ks n on h. And we know that this is 1 and this is also 1. And if we take any other monomial, m prime, any other monomial, then either here or here will be 0. So we get exactly what we want. And it doesn't matter how we choose this alpha case, beta case. Our only goal is to find this alpha case and beta case so that to obtain a cycle. Of course, we cannot take a chain which is not a cycle. It is not a homology class. Okay, so is this more or less clear? The matter is, well, let us be sure that this is clear. And now I want to explain how to correct our Z1 to obtain this Z. Okay. Okay. Now let us let us start correcting this Z1. First, we make it in several steps. The first step is separate. It is distinguished, but all others will be similar. Well, first step. We see that dz1 equals this. Well, I prefer to write it in the following form. I want just to simplify notation, okay? This thing which is circled by this line, this all will be denoted by eta I. It is an element of here in bar resolution of the group Q. Just I want to include this coefficient to it. Actually, it doesn't matter where to include this coefficient. I can include, and this element will be zeta I. Okay? Just I need some notation. No, not this element will be zeta I. Zeta I. To think about, well, let us look on this particular element, h minus h to the power, to any power in Q. I claim that this element is 0 in homology. It is not true that it is 0. Okay, this is an element of first term of bar resolution for free group, and we take coinvariance. This complex, where if we take B star here, it computes the homology of free group. But I claim that this element is trivial in homology. Why? Because these two elements are conjugate. Look. A priori, initially, I don't know that they are conjugate in F n minus 1. But I would like to recall that here it is important that all relations in pure braid group, we have written them explicitly. All relations are trivial in commutator. So and what does it? Well. Oh no, this is not important. I'm sorry. Just what I want to say, that One moment. Что у меня написано? Yes. Okay. If I write down this conjugation, qi minus 1, yes, h, q, i1, h and q, i1, okay? We know that there are counted homomorphisms. We can compute how many, since all relations lie in the are trivial on the commutator, so all relations counting homomorphisms are well defined. We can count algebraic number of any generator here. Look, which generators are here. This is tau ksn. This is this is an element of this free group, and we have here one element ksn and zero number of other generators. Well, so we know that this one is conjugate in Fn-1 to H itself. Okay. This is the same as to say that this group acts trivially on abelianization of this one. Since it acts trivially on abelianization, it definitely takes H to a conjugate element. It cannot take H to an element which is not conjugate to it. Elements are equal to oh, so sorry. Why conjugate? Well, I'm sorry. It's my English. Conjugated is not the correct word. I mean quite different thing. No reason for it to be conjugate. I'm very sorry. What I want to say that these two elements they are equal after taking quotient by commutator. This is true. So H and HQ to any power, it doesn't matter what is here, are equal in if I take the quotient of f by its commutator, which is just the free abelian group. And of course, well, here counting homomorphisms are well defined, and of course we have here identical number of all generators, so this is true. Okay, I'm sorry. I forget what the word conjugate conjugation is not the correct way. Okay, and hence they are equal in homology. This is exactly first homology is just the abilization. So if two elements are equal after taking quotient by commutator, then they are equal in homology. And hence, since they are equal in homology, we know that their difference is a boundary in this complex. So I can write that this difference is boundary of some chain, which I denote by zeta I, and this zeta I is element of second term of bar resolution, coinvariance. Okay, well, that is true. So what we can write, we know that dz1 equals, okay, we have written it in the form sum over I, zeta I tensor, no, I forget about shuffle. Shuffle of zeta I tensor eta I, where zeta I have degree 2 and eta I have degree s minus 2. Now I want to make first correction. I want to say that I take zeta 2, which is equal to zeta 1 minus, and here I want, sorry. This is, I'm very sorry. Here I have d zeta 1, tensor eta I. And this is, here I have just this element, and this is d zeta I. So, but I would like to add the following correction. I would like to take shuffle, and now without d, zeta I tensor eta I. Okay, what is the result of this correction? Well? No. With half. It's very important. Look, if I take here, I want to compute the boundary of this zeta 2. When I compute the boundary of zeta 2, well, I know the boundary of zeta 1 is here, and I need to take the boundary of this one. The boundary of this one, I have three terms: this one, and that one. Look, the first term exactly cancels with this one. So only these two terms survive. But here, the only thing what I want, the only thing which is important for me, that here I always have degree 2 on the left and degree s minus 2 on the right. In both terms, I always have, I don't want to write down them explicitly. It doesn't matter how they look like. The only thing I want, that the result is as follows, that it is sum of some kappa I. Well, first of all, it is sum of some shuffles. All elements here are shuffles. So it is shuffles. And here I take some kappa i's, tensored some mu i's, where kappa i's live again in kappa i's live. There are two chains in this free group, and mu i's are s minus 2 chains of Pn minus 1. So this is the only important thing for me. Now, this was the first step. So look, before the first step, I have here one chains and s minus one change. After the first step, I have two chains and s minus two chains. And so on. All further steps will be identical. And so I want to say that I want to describe arbitrary step rather than the second. I want to clear this. So I claim that before, and once more, it is important that here I have also shuffles of two chains with s minus two chain. As I promised, I add here only shuffles with first. So before, after k minus 1 steps, I claim that after k minus 1 steps, I will have the following situation. That I have zk, which is of, first it is of this form. So we added only, we have zk, which is z1 plus shuffles of something of degree greater or equal to 2, tensor by I'm sorry for writing like that, but I don't want to introduce more notation. So first of all, zk has this form. And second, I know that dzk has this form with some kappa i's and mu i's, where degrees of kappa i's are k. So after the first step, I have here degree 2, but after kth step, k minus 1 step, I have degree k. And I claim that I can make one more step to increase this degree by 1. Okay, let us do it. Here all steps are similar. First of all, let us look on this writing. All our complexes, I recall that these kappa i's are in bk of f in minus 1, coinvariance n minus 1. Yes? Mu I are in B s minus k minus 1, since this is dz, of Pn minus 1, Pn minus 1. Well, all these coinvariant groups are free groups, free abelian groups. If I take Bayer resolution, then its coinvariants are just, I know its basis, it is free group. So here, inside shuffle, here inside, this is an element of tensor product of two free abelian groups. And of course, I can rewrite it so that mu i's are linearly independent, that they are part of basis. I can rewrite it so that I can take for mu i's just standard basis of bar resolution. Well, and group all elements with this particular mu I. So I may, I can assume that mu i's are linearly independent. Well, why I need this? I would like to compute differential of this differential. Of course, twice differential is 0. So I get that 0 is this. And now I want to apply that once more, apply that formula. What I get? Look, I want to write the first term. The first term is its sum of shuffles of dki tensor mu I. And I don't want to write all other terms. I want to write dots. The matter is that, look, here we have k minus 1, degree k minus 1. So we have k minus 1 elements from H and corresponding number of elements from P. And in all other terms, I will have k elements from H and other elements from P. These elements cannot cancel. In bar resolution, we have no relations. This is not in homology. This is just in bar resolution. So I know that this is 0. Well, and again, these mu i's are bases. So these elements cannot cancel with each other. So I can claim that these dk kappa, each kappa I is a cycle. So the only possibility to have 0 here, but we must have 0, is that d kappa I is 0 for all I. Well, and now, up to now, we almost not use the specific of our groups. But now we want to use it. We know very well the homology of free group. And what is the homology of a free group? It is only one-dimensional. It's the homology of wedge of spheres, of circles. So, but these kappa I are k dimensional with k at least 2. So we have no homology in this dimension. So what we can say, that since kappa I is a cycle, then it must be a boundary. So we know that kappa I is the boundary of some theta I. Well, and we again get in the same situation as here. But the reason is different. The reason why here is the boundary is different. But now we can rewrite it as d theta I, and we can use the same trick. So we may take for zk plus 1, zk minus sum over I shuffle of theta I without boundary tensor mu I. Well, that's all. So in finitely many step, we get that 0 here, since we of course have no negative gradient, and so we get 0 infinitely many step, and so we on any step, well, first step we add here was 2s minus 2. Here it is k plus 1 and s minus k minus 1. So second step we add shuffles of 3 and k minus 3 chain, 4 and k minus 4, and so on. Well, and we arrive to a homology class. Well, now, what we have proved? We have proved that, up to now, we have proved that there are no other relations, and there is dual basis in homology. Now we make a break. After the break, I will very rapidly I will explain why they generate the whole cohomology, and after that. After that, we start discussing Hochschild-Serre spectral sequence, and actually, this topic was just. I want you to see that we haven't say spectral sequence here, but in fact, we more or less compute differentials of the spectral sequence, and when we look on general construction, I hope this computation can help us to understand this. Okay, so now let us make a break, well, till 6. Okay. Well, let's proceed. First of all, I want to say that what we have made now, just what we have just made on the previous part of the lecture, it is very standard philosophy for spectral sequences. We try to write down something natural, which was Z1. It is not a cycle, but it is a cycle up to something. And then we move along some filtration. Now filtration is by degree of these elements. And we make that it is cycle up to elements of further and further and further of further and further and further degree. And finally we get a true cycle. And in another phenomenon which is also very, very typical, I just want on this, is that differential in spectral sequence is very often something like going by such zigzag of delta and delta inverses. Here we always understand that something is boundary of something. This ki becomes boundary of theta. We use something to understand that it is boundary. We took, and this is we go by delta inverse, and but if we look how this mu are provided, they are provided generally mostly from this term, but also, and this is something like taking taking differential. So in some sense we alternate to take. In some sense we take the inverse of differential, and in some sense differential. And this is very typical, and we soon see its general situation. But at the moment, let us forget about spectral sequences and let us just finish the proof of the theorem. The matter is that we still have not proved it in full generality. The matter, we still do not understand why these omegas generate the whole cohomology ring. This can be proved using some explicit formula similar to this, but I don't want to do this since it is cumbersome, but this is very easy fact from what we already know. The matter is that I recall maybe I will not be very precise now, but okay, I just give more or less an idea, but it can be made precise very easily. I recall that we have started last time we have discussed what is the space K by Pn, what is the classifying space for pure braid group, and we proved that it is the space of ordered configurations, of n points in R2, and the short exact sequence which we discussed, it corresponds to the following fiber bundle of K pi of Eilenberg-MacLean of classifying spaces. Namely, we can consider the configuration space of n points on R2, then we may forget the last point and get into configuration space of n minus 1 points in R2. And here the fiber is just R2 with n minus points deleted. Well, we know that this fiber is homotopy equivalent to n minus 1 to wedge of n minus 1 circles. Exercise, I don't want to do it in details, but it can be done. I prefer to leave it as a good exercise. We can replace these spaces by homotopy equivalent and map by homotopy equivalent. We can replace all this figure up to homotopy equivalent so as to obtain true fiber bundles with this fiber. So we may realize classifying space is always defined up to homotopy equivalence. So we may realize configuration spaces so that the fibers are true wedges of circles. So we may realize it so that this is some particular realization, so that the fibers here are true wedges of circles. But then I'm sorry. I again. In mind, I always try to reverse the roles of fiber and base. I'm very sorry for this. I didn't thought it through in correct formulation. I'm sorry. Well, the matter is that actually we can find a CW decomposition here with as many cells as we expect here, but I'm afraid that in this situation, it would be very easy if the base was wedge of spheres and the fiber was something, but in this particular situation, I'm sorry, when I was prepared to this lecture, I decided that it is very easy since the base is wedge of spheres, wedge of circles, but this is not true. Well,
maybe it's true for KP1 bar, then we can leave it.
Well,
it's true, no, KP1 bar, it is, what it is? It's one circle, yes?
yeah. But then on this step, we have something complicated here, and to understand that, yeah, actually this is, well, okay, I have reached my main goal. I explained why these classes are independent without any. Actually, there is the following. Actually, there is the following main general fact, which we will see from spectral sequence when we discussed it. The general fact is that for any that for any fibration like that, ranks of homology groups do not exceed ranks of homology groups of direct product. Direct product is, well, and actually from this we can see this. If one managed to reach here that we have, in fact, okay, what we can expect here, that the number of cells is these cells below, they are multiplied by cells above, and they are glued in some maybe strange ways, but the numbers of cells is prescribed. Okay. Let us. I just want to say the result at the moment. That actually, I have already said it on the previous lecture that the Poincare series. The Poincare series for this configuration space or for Pn is what is the Poincare series? It is just it's just some series in formal variable t whose coefficients are ranks of homology groups. Actually, Poincare series exists over some field or over Z, ranks or dimensions over field if we take coefficients with field. But in this particular case, actually, if we manage to obtain here this very good cell decomposition, then we just see that this is series for coefficients of t to the power k is the number of cells in dimension k. So from it can be understand that a rank of, and even not rank for generally for finitely generated abelian group, rank is usually the rank of free part, but I just want to say about the number of generators. So I just would like to say that the number of generators of the total homology group, just of the direct sum of all homology of Pn, or I can say of kth homology group. The idea is that it is less than or equal than the coefficient of t to the power k in this coefficient of t to the power k in this series. Actually, this is because, in fact, one can find cellular decomposition with exactly this number of cells. So we cannot have more homology than cells. But this is already enough. If we prove this in some way, when we will discuss Hochschild's third spectral sequence, I will show that it is immediate from it. But at the moment, let us skip detailed proof. But well, from this, it is indeed immediate. Further, it is very easy. The matter is that the number of such monomials is exactly this coefficient. Look, we have here. It is easy combinatorial easy combinatorial computation that the number of monomials where Li's are strictly increased and Ki's are from 1 to are less than K, then Li's, this number is exactly this coefficient. So we have already constructed such number of homology classes and such number of cohomology classes which pair off with unit matrix. So which are dual bases to each other. It is important. So I claim that it is that all the homology and all the cohomology. Why? Well, we have constructed. Let this be some number q. Well, for qk. We have constructed z to the power qk in homology. And we have constructed z to the power qk in cohomology so that they pair off with this unit matrix. It is important that this matrix is unimodular with determinant 1, not only non-degenerate is not enough, but it is unimodular. Well, they pair off together. Is it possible that this cohomology group is actually greater than this? So is it possible that we have strict inclusion here? If we have strict inclusion here, first of all, we cannot have more generators here. So what is the only possibility? The only possibility, how can a free abelian group be a subgroup, a proper subgroup of the group with the same number of generators, of an abelian group with the same number of generators? The only possibility is that this is also free abelian of the same rank, but okay, free abelian group can be embedded into another free abelian group in a proper way. But then the pairing between these two groups would have not integer determinant. If we have a proper subgroup, then the determinant of this pairing is the determinant of this pairing multiplied by the index. So here determinant is 1, so it is not possible to have this situation. Well, so indeed, this is some idea how it can be proved, but indeed in this situation it doesn't, I don't want to describe it explicitly before we, so now we discuss spectral sequences, and after that we see that first of all that what we did here can be made, can be done using that machinery, but and also this part also can be done using that machinery. In fact, why I could start from spectral sequences initially and don't tell all this stuff, but actually the matter is that I want to stress that all these steps can be made completely explicitly. I didn't make it completely explicitly. I didn't write these theta i's explicitly, but in each particular situation, I could do this. It is not so hard to write them down, and this is how the differentials of spectral sequence sometimes can be computed. General philosophy is that differentials of spectral sequence usually cannot be computed in most cases. But I would say that in group theory, they can be computed in more situations than in topology. So we still have some hope, and something can be made explicitly. Okay, now I want to erase everything and to start with more consecutive explanation. So today we discuss spectral sequence of double complex, and then we apply it in the situation of Hochschild-Serre spectral sequence, but probably this will be next time. So the main object for us is double chain complex. What is this? Usual chain complex is sequence of groups indexed by integers with differential such that square of differential is differential can decrease the gradient or increase the gradient. One situation is taken to another just by reversing the gradient. So at the moment I assume that it decreases the gradient. But now we want to have double complex. This means that we have two differentials. The first differential decrease, the first will be d prime and the second will be d2 primes. The first one decreases the first gradient. The second decreases the second gradient. And now, the most important part is that these differentials commute or anti-commute. This is, well, these are two possible conventions. We may either require that these differentials commute or require that they anti-commute. There is completely no difference between these two situations. Actually, when we work with chain complexes, we usually are interested in something like homology. Homology doesn't change if we reverse the sign of a differential. This situation, well, we can, for instance, reverse the sign of every second vertical differential. And we get from one situation to another. All homologies and so on doesn't change. So these are actually, this is actually a convention, this is not substantial difference. This is just a convention. In different situations, different conventions are convenient. First convention is more convenient if we want, how can we think about this object? We can think of it as of chain complex of chain complexes. So each vertical row, column is a chain complex, and here we have chain maps between them. Then, of course, chain map is what satisfies to this one. Similarly, we can consider rows as chain complexes and vertical maps as chain maps of chain complexes. Then the first one is more convenient. But the main example, main source of examples is often double complex, arises as tensor product of two chain complexes. So where tensor product can be over something, over some ring. There are different possibilities. This is just not one particular example. This is some source of examples where AP and BQ are usual complexes. And then it is natural to consider well, differentials here are induced by differentials here, and here it is natural to use standard convention that when we apply differential to the second guy, differential has degree 1, so when it goes through the first guy, we obtain -1 to the power p. And then with this convention, we get into the second convention here. So sometimes one is more convenient. In other situation, other is more convenient. So it is better just to understand that we can choose whatever is convenient to us. Today, I will mostly, this is just, well, I like this convention more, but it is, by no means it is better. Both are possible, both are good, and it is better to go from one to another whenever it is important for me. Why I prefer this one? The matter is, okay, there is one important, from a double complex, we always can construct its total complex. Total complex of D is, by definition, it is usual chain complex. The nth group of this double complex, well, of course, I forget to say that, of course, all these are abelian groups. This is abelian groups or some modules over, but definitely. Okay, this is just sum, a direct sum over p plus q equal n of d pq. And I want to introduce the total differential in this complex. And here this convention is more convenient. In this situation, I just take the sum, and then the square of this differential is 0. If I use the first, this is in the case of the second convention. In the first convention, I must say that if I compute this total differential on A tensor B, where A has degree P and B has degree Q, then I get sorry. I again think about this example, but by no means, if I take the total on A, which has by degree PQ, which belongs to, by degree means that A belongs to dpq. Then we may introduce it in this way. Okay, again, both conventions are possible, just the first one is easier in this place, but others are easier in other places. Okay, so and what is spectral sequence of double complex? First, not what is, what do we want? We want to express homology of total complex from something which from the double complex itself. So what we can do immediately? We can forget about one of differentials, and we can compute the homology of double complex with respect to differential d prime. This is one object. We can compute the homology of double complex with respect to the differential d2. And we would like to express the homology of total complex from something like that. Okay? This is our goal. And now, well, Just we can consider the same double complex. We can forget about these differentials and just compute the homology of every row with respect to the first differential.
So it is a row of...
Just take, we have double complex. We may take any row of it and compute its homology.
Yes.
So in each situation, in each place, we would have homology group. We would have such table of this homology group. But in the second row, we also have homology.
So it is a set of homology.
Yeah, well, it is, yes, we can consider H, P, Q. It's homology group in dimension, in B dimension PQ. But now we, each Q is treated separately. Q is just index which numerates this group. We have nothing substantial in this. But we have similarly considered this one. But what we are interested in, homology of total complex. And we would like to express them in some way from, well, yes, of course. Not only they can be different, they have no relation to each other. They are, well, they live in completely different worlds. Okay, but what I wanted to say, well, I would like to consider one simplification. Actually, there are. It is not so easy to follow here. Look, generally, if you have chain complexes, its indexes can go to plus infinity and to minus infinity and so on. And then it is possible that there are infinitely many groups in this sum. We can have over. I don't want to consider such situations. So let us. It is possible. There are still good spectral sequences. Just I don't want to think about it. I want to describe spectral sequence in some easy situation. And actually, this situation is most important for us. The matter is that I mostly will be interested in such examples where these are some usual complexes, such as, for instance, some resolution and so on. We usually have chain complexes which are non-negative. So I would prefer to say that one possible assumption is that our complex is non-negative. So this is 0 unless both P and Q are non-negative. So if at least one P and Q is negative, then the group is 0. But actually, in some situations, this assumption is not true. Namely, sometimes we are interested not in chain complexes, but in cochain complexes. What is cochain complex? Differential increases the gradient. Then, to get into this situation, we need to reverse the gradient. If you would like to apply some construction with reversing, with decreasing differential to complex with increasing differential, then we just need to reverse the gradient, but then we get into opposite situation. Actually, important only that for me it is important. The only one important thing is that on each diagonal we have finitely many non-zero groups. So the only important thing is that we have finitely many non-zero groups on diagonals. So it completely doesn't matter. We can have this unless only we can have complex concentrated here, or we can have complex vice versa concentrated here. The only important thing is that each diagonal crosses it in finitely many groups. But for simplicity, I will assume this one. But it works without change in the other situation. Okay. Well, let us just let us start with the following. How does a homology class of total complex look like? What is a homology class? A homology class is cycle up to boundary. Well, we consider groups of cycles but what is a cycle in this situation? Look, total complex, nth gradient of total complex corresponds to such diagonal. Well, and if I, what is, I prefer to have dots here, okay. What is a cycle? So an element of this total complex is something like that we have here. I will, for each element, I will write index which is by degree. So we have y0 n, y n minus 1, and so on, n0. So any element of this total complex, of nth group of this total complex, is sum of some elements in these cells. Well, when it is a cycle, we may apply d2 primes here and d prime here, and we get into this cell. Here we also have d2 prime and d prime, and in each cell we can sum the corresponding two elements. And if we have zeros in all cells, then it is a cycle. Well, so condition for cycle is that, okay, d2 primes of each ypq equal to plus. In my convention, in this convention, I need to write plus d prime of y p plus 1 q minus 1. It must be 0 for all p and q. Okay? What is a boundary? A boundary is such an element that there exists here, let it be x. Oh no. Okay, x 0 n plus 1, which goes to here, and again similarly we have such sequence of x's in these cells, such that well, I don't want to write it by particular expressions, but again I need to go from here and to sum them, the results, and I need to get this particular y. Okay, what is the idea of spectral sequence? I want to start from idea rather than from the result. The idea is that we can approach to this total situation in the same way as we have approached cycle condition in our previous computation. We may consider elements which are not true cycles, but which are cycles up to some filtration. Namely, so I would like to give a particular definition. consider some cell PQ, and I would like to look on one cell. And look, I will say, okay, first of all, I want to step on, assume that we go to 0 here. Each cycle, if I have a true cycle, it always starts somewhere. We can have several y's here, can be 0, and further non-zero. This is just this first place where it is non-zero, so I assume that here we go to true, here we have true 0, so this d2 prime is 0. This is the last. In general situation, this can be this last. This is 0 by dimension reasons, since we have this assumption. Okay, but then I am interested in the following. Is it possible to this ypq is generally not a cycle of a total complex? It is, if d prime also 0, then well, this ypq is itself a cycle of a total complex. But generally it is not. My question is it possible to change this ypq but by elements of smaller gradient? Smaller gradient for me means elements which are closer to the left, which has smaller p. Is it possible to add these elements to make it a cycle? And I want to approach this element, this property step by step. So I want to ask to the following: whether it is possible to find here next element and next and so on up to some okay, I would like to have r elements here. So here will be y with p minus r plus 1, q plus r minus 1. And I'm interested whether it is possible to find elements here so that if I sum the result here, I get to 0. This notation means that the sum of this result is 0, not each of them. And so on, and here also the sum is 0. And through the whole, but I do not assume anything here. So, okay, and I would like to say that, okay, this ypq is good on step r if it is possible to find such sequence. If an element is good on all steps, then I am able to make a true cycle. But, okay, the set of all y's which are good on step r is denoted by z r pq. Pq is just this place. So this is by definition is the set of all ypq in. I would like once I want to write it explicitly. So it's one pq in this group, such that first of all there are true cycles for d2 prime. This is 0. And second, we can find these elements so that, and second, there exists y p minus pi minus 1 q plus 1, etc. y p minus r plus 1 q plus r minus 1, such that any of this sum d prime of y pi minus s q plus s equals d2 prime of the of next. Oh, again, yes, well, their sum is 0. Yes.
We use the second notation.
Yes, yes. We use the second notation, this one. Hence it's 0. In the first notation, it would be 1 equal to n. This is Z. Well, what we know about these groups Z? We, of course, know, here we do not assume anything. So, well, okay, what we know? We know that, of course, these groups become smaller and smaller and smaller. Well, if we assume that there are such elements, it is more, we assume more than if we assume r minus 1. So we have the first such group. And look, the first such group, we do not assume the existence of any y. The first one is just the kernel of d prime, the d2 prime. Kernel of d2 prime, of course, in this by degree. And we have the 2pq, the 3pq, and so on. And of course, we have the intersection of all these groups. And this intersection is usually denoted by z infinity bq. But I would like to stress that we have no limit here, actually. In each diagonal, it is finite. We assume that our complex is non-negative, so in each diagonal it is finite, just the number of steps is different for different diagonals. But for each PQ, it terminates infinitely many steps. So this is not any limit, but this is just, this sequence just stabilizes. Okay, so these groups, and look, these are true cycles which starts from this place. Yes? So these groups can be considered as some approximations for cycles. These are cycles up to something. Now I would like to introduce approximation for boundary. Well, I would prefer to draw it here. So again, I would like to start from some ypq. Okay, and look, one moment. It would be nice if I find here x p plus 1. It's x p q plus 1. If I find here an element which goes to it by d prime, it is a very good situation. Why? This ypq is not itself a boundary, but it can be easily made a boundary by adding the boundary of. So it is a boundary up to terms of smaller filtration, or up to terms which are more to the left. Okay? So if I has this element, so this is the best situation. This y is definitely can be made a boundary just by adding here d prime of this x. So this is but okay. Actually, maybe let us start with this. This is bpq 1. It's just as here, it is kernel of d2 prime. This is just image of d2 prime. Okay? So it is naturally dual to that one. But now I would like to say, okay, it is also not so bad if I cannot find such x with which immediately gives us y. But sometimes I can find 2x here and here. Okay? But if I have no additional requirements, it is not so interesting. Yes, so that they together give y. But if I have no additional requirements, it is not so interesting. The matter is that, okay, then I can, starting from this ypq, I can make it a boundary by adding this and this, but this one is of larger filtration. I would like to filtrate everything from left to right, so it is not so interesting. But it is interesting if this one goes to 0. So such ypq for which there exists such picture, this is b2 pq, which is greater than b1 pq. And now I write general definition for brpq. brpq, I have r elements here. So x, oh sorry, here I have p plus 1 q, and so on. If I have r elements here, then the last one will be x pi p minus r plus 1, and here I have q plus r. Okay? This is the last one. And the requirement is like that this goes to 0. And here, if I sum the results, I always get 0. So this is an exact definition. BPQR is the set of all ypq in this double complex such that there exists such picture, such that there exists x p plus p comma q plus 1, etc. x p minus r plus 1 q plus r. Oh, sorry. Sorry. This is not the correct. I'm sorry. Q
No, that's
p plus r minus 1
yes.
and q minus r plus
No, not
2.
plus 2. Yes.
Well, and I'm sorry. It is always better. I prefer to write pictures than to compute this. And actually, it is better to write pictures than to compute this indices. But so I assume that there exists such x's such that the last one is killed by d2 prime. Well, for all previous, we have d prime of x well, d prime of x next. I'm sorry, I don't want to plus d2 prime for x previous is 0. I don't want to write this for all except for the first one. And in the first one, in the first situation, I will write it explicitly. D prime of x p plus 1 q plus d2 prime of x p q plus 1 is ypq. So again, if it exists up to now these groups, vice versa, the more R we take, the greater is this group. Well, so but I claim, again, we have this limit group, which is in fact not limit, but just one of these groups, they stabilize.
Sorry, could you repeat please why it becomes greater?
Well, the matter is that if we are in BPQR, then we can just take the next element, just take 0. And we have the same picture for okay. But I also claim that we have this inclusion, that each B is strictly smaller than Z. And this is very easy. So I explained all these inclusions, so why this inclusion is true. This is very easy. Indeed, if we have any such sequence, then we can add to this, we can consider this ZPQ. Well, here we put D prime of X PQ plus 1. Yes? And here we put just zeros. And I say that these two elements, they are true cycle. They together they are true cycles. A true cycle. Indeed, if we go to look any such YPQ, if we apply D2 prime to it, this YPQ is sum of D2 prime of something and D prime of something. Well, if we go twice along D2 prime, we get to 0. But if we take the D prime of this one, it is the same as we go through here. Well, and here we have, so we have twice D prime. It's again 0.
But doesn't it explain that the infinity lies in Z2, not in Z infinity?
No. Z2 is, this is not this, here is 0, here the sum is 0, well, but here is also 0. Z2 means that there exists this element without any requirement here. But if we have a requirement that goes to 0, then we can add zeros here. And so we are in all Z's. So we actually have this inclusion. Okay, and now this is this filtration, these two filtrations in groups. This is central object of spectral sequence. Now. How many? We need to stop at some moment. Yes, not just now, but okay. So the central object of the spectral sequence is the quotient groups. We can consider such groups ERPQ, which is by definition the quotient of ZZs by ZBs. Well, usual homology are quotients of cycles by boundaries. Here we take almost cycles by some smaller number of some restricted boundaries. Okay, and these ERPQ, they become smaller and smaller and smaller and smaller. Okay, and first claim is that the limit situation is E infinity PQ, which is Z infinity PQ quotient by B infinity PQ, and again we have no, we do not need to pass to a limit. It is just some particular step which depends on PQ. First claim is that these groups are closely related to homology of total complexes. And second claim is that, well, these groups are called, well, there are several different terminology here. Sometimes it is called rth term of spectral sequence. Sometimes it's called rth page of spectral sequence. Sometimes so there are sometimes rth sheet. So I can't understand which terminology is better. It's the question of English, not of mathematics. But and okay, the idea is that these terms approach and approach and approach to something which is closely related to homology. Now let us understand how this is related to homology of the total complex. But before, let us just understand what is E1. E1 PQ is very easy. Okay, it is just enough to look here and here. And we immediately see that E1 PQ is just this homology group with respect to differential D2 prime. So this is what, as I said, the main ideology is that assume that we understand what is this, and we want to arrive to something, to homology of total complex. Okay, so we may assume that E1 is known for us. And we would like to proceed up to, but now let us consider the final term. So now, now I prefer to start with formulation. So claim about this infinity term. Claim is that there is the following filtration in homology of total complex. F0n, smaller, all inclusions are non-strict, Fn1 n minus 1, and so on. Well, next is F2n minus 2. And the last one, Fn0. Fn0 is it's some strange idea to write this indices on above. Of course, it is below. Fn0, which is the total, the nth homology group of total complex. Well, now, claim that there exists such filtration. But I will construct it explicitly in a moment. There exists such filtration, such that if I take the quotient of the next by the previous, F PQ quotient by F p minus 1, q plus 1. Then it is exactly this limit term of spectral sequence. Well, and let us assume that the previous term is 0 here. So this is claim. And now let us understand how to construct such filtration. The construction is very easy. FPQ is by definition consists of all homology classes. Well, any homology class can be represented by a cycle, by a sum of such y's, which lie each in. But FPQ is those homology classes of degree p plus q that can be represented by a cycle which is not whose first coordinate doesn't exceed p, so which has zeros in all these places. So to be precise, FPQ is subset of homology of total complex. All homology classes that so all homology classes that can be represented by such elements of type up to PQ. Of course, P plus Q equals N in all these groups. Well, so without anything else. So all these elements only up to here. Without. Okay. This is just I want to say that of course the same homology classes sometimes can be represented by elements with enters here. This is just existence of such a representative. Okay, and now this is very easy. Let us understand that this is more or less obvious. Okay, first of all, by definition, I have here, this is just definition, yes?
Sorry, those Y's are whom?
Yij lies in Dij. Just any elements, yes. The crucial thing that there are no elements with, which are to the right of P. There are no elements in, well, but it is immediate from definition that this equality is immediate from definition. If I allow elements in all positions, then this is just not a restriction. Any homology class can be represented by a cycle. But generally, we need elements in all positions, in all diagonal positions. But sometimes it is enough to take only several first of them, then we get into smaller filtration. Okay, let us understand this one. I want to construct the following homomorphism. I want to construct, let it be here. I want to construct a homomorphism from Z infinity PQ, from this numerator, to this quotient group. And then I I would like to see that the kernel is exactly, that this is surjective and the kernel is exactly B infinity. Well, how to construct this? Okay, let us recall what is Z infinity. Z infinity means that we have this sequence of, this is the set of all y pq such that there exists the sequence up to the end, up to the end. Okay, so look, if for such y pq there exists such sequence, then I just take y pq to the, look, the sum of all these y's is a true cycle of total differential. So I just can take y pq to the sum of all this. So look, I would like to take y pq to the homology class represented by the sum of all this sequence. Well, what I need to check? I need to check, of course, here there exists such sequence. I could found another sequence of this type with some other elements in these boxes, and then I get another homology class. So, but this first y, it is fixed. I can get, so here it is pi minus p minus 1 q plus 1, and suppose I have another, some p minus 1 q plus 1 with primes, and so on. Well, but then look, the difference between these two belongs to this denominator. Since it is represented just by construction, it is represented, these two cancel, and it is represented by something which lies only in these boxes. Well, so what we see? We see that this homomorphism is well defined. Its value is independent on this sequence. So this sequence exists, so we always can do this, but then it is independent of the choice of this sequence. Okay, and now, now I want to understand that it is surjective. It is completely immediate. Any element in FPQ can be represented by such sequence. Okay, then YPQ goes to it. Okay? Any element in FPQ, by definition, is represented by such sum, or sum of such form. Then YPQ belongs to Z infinity. And okay, now I need to understand that the kernel of this phi is exactly B infinity. Okay? Well, what is B infinity? B infinity are such elements YPQ that there exist x's, there exists picture like that. If it is like that, then well, it must be very easy. This YPQ goes just to sum of this and this. just well. If we have such sequence of x's, well, сейчас что-то должно быть совсем очевидно. Well. Well, yes. If we have such a sequence of x's, then this class inside is just ypq plus d prime of x of this x. But this is a boundary. This is just trivial homology class, since it is total differential of the sum of these x's. It is just by construction, it is completely trivial, I'm sorry, of these x's. Well, just by construction, this total differential, so it is trivial homology class. And, well, let it be an exercise. It is that there is no reason for this. Is just simple diagram things like that. A good exercise that kernel of this phi is exactly B infinity. We understand why B infinity is in the kernel. It is as easy as we have done that kernel of phi is exactly B infinity of PQ. That if we are in the kernel. And so we arrive exactly to this. So we see that if we know E infinity, then we not know exactly the homology group, but we know these consecutive quotients. And this is rather a big information about homology groups. Sometimes it is enough, sometimes not. But at least we get some information about homology group. We understand that for this homology group, there is filtration such that the sequence of quotients is as we obtained. So now the only but the most important part is that we want to pass from E1 to E infinity. So we see that E1 is something more or less which we know, and E infinity is something close to homology of the total complex. Now I just briefly say the idea and we finish, and next time we proceed. The idea is that if we have a finite sequence ZPQR from ZPQR, so we have sequence up to here, and nothing, and we do not know anything about this value. Well, then we may assign to such sequence this value. To such a sequence, it is natural to assign this value to it. And if we have an element in ZPQR, then we can get into box with numbers p minus r, q plus r minus 1. And if we think through this construction, then actually we get a well-defined map, which is denoted by dr. This well-defined map is from E. I said that it is from ZPQR, but this group will be in its kernel, and actually it will be a map from EPQR to E with this number, P minus R, Q plus R minus 1, R. This will be a differential, and the most important thing in all these spectral sequences is that the R plus I first term of spectral sequence is the homology of rth term with respect to this differential dr. So the picture is as follows, that the first term is obtained from here, and each next term is the homology of the previous term with respect to certain differential. And so we may proceed up to infinity, and then it is very close to the homology of total complex. And well, this will we will discuss this next time. So I hope that I more or less explained you why this is true, why the infinity term is close to homology. And now let us finish for today. That's all.